When collecting data, no matter how well we plan, no matter how much data we collect, we rarely see normal behavior. As a consequence, the standard capability indices do not give valid information because they are based on the normal distribution. In preparation for dealing with possible non-normal data, we should first examine the histogram of the data. If we see the histogram is centered within the specification and falls well within the specification, then it is likely to be capable. If the histogram does not exhibit these characteristics, the data is likely not normal. We can attempt to make non-normal data appear to be normal through a transformation. Finding the ideal transformation is not easy to obtain. A common technique is the Box-Cox power transformation. This transformation entails raising the data to a power, lambda. Lambda can be positive or negative and optimized based on our effort to maximize the correlation between the transformed data and the percentiles of the normal distribution. If lambda is 0, we revert to the logarithm transform. We can also optimize lambda by maximizing the logarithm of the likelihood function. This function and the process is very complicated and best left to Excel or statistics software. Other types of transforms include the log transformation, the exponential transformation, and the reciprocal transformation. Let's consider this example. As we see, the data is clearly not normal. The histogram shows the data is heavily skewed to the right. Let's prepare the data for a Box-Cox power transformation. Excel will be used for this operation. First, the data is sorted in ascending order. Second, the Box-Cox power transformation is performed using the formula on the previous slide. Pick a random value for lambda. We will use the goal-seek function to optimize. When we generate the normal probability plot for the X data on the horizontal axis against the normal percentiles on the vertical axis, our finding of non-normality is affirmed, based on the manner in which the data does not adhere to the best fit linear line. Now, use Excel to calculate a correlation coefficient between the transformed data to the normal percentiles. Remember that these are z-scores that separate a bottom percentage from an upper percentage under the normal curve. Our optimal lambda is determined when the correlation coefficient is maximum, or 1. Using the goal-seek, we obtain a lambda of 0.2796. Now look at the refined normal probability plot for the transformed data against the normal percentiles. We now see that the data conform to the best fit line in a much more favorable manner. This is indicative of a normal behavior of the transformed data. A summary of the transformed data is shown in the table. Each data value is raised to the 0.2796 power.